Good morning, everyone, and a warm welcome to all of you. It gives me great pleasure to welcome you to this special session organized by the Feynman Club. We are thrilled to have all of you here as we continue our journey of exploring the wonders of science through engaging discussions with experts in the field. The Feynman Club started as a humble reading group where students gathered to discuss the renowned lectures of Dr. Richard Feynman. Over time, it has evolved into a platform where eminent scholars from across India share their research and insights, fostering discussions that inspire students to delve deeper into the realm of physics and scientific exploration. Our goal is simple: to create a space where students can interact with experts, broaden their understanding, and cultivate a deeper passion for research. Today, we are honored to have with us Mr. Philip Cherian, a physicist with a diverse academic and research background. Philip completed his undergraduate degree in physics from St. Stephen's College, Delhi University, and pursued his postgraduate studies in theoretical physics at both École Polytechnique and École Normale Supérieure in Paris. Apart from his work in physics, he has a keen interest in the history of science and was a research scholar at Columbia University, where he contributed to the Making and Knowing Project, a research initiative exploring the intersection of artistic making and scientific knowledge. From 2017 to 2020, Philip worked extensively with the physics department at Ashoka University as a teaching fellow, where he played a key role in developing undergraduate laboratory courses. In 2020, he was also a visiting faculty of physics at the Young India Fellowship. Currently, as a graduate student at Ashoka University, he is working on modeling the spread of COVID-19. His research interests span astronomy, epidemiology, and improving science education at the undergraduate level. It is an absolute privilege to have him here today, and I'm sure we are all eager to hear from him. The advancements in camera sensors and amateur telescopes have transformed observational astronomy, making it accessible even to amateur astronomers working from their own backyards. In this talk, Philip will introduce some of the experiments he has helped design for an introductory astronomy laboratory at Ashoka University. He will begin by discussing basic techniques in image reduction, stellar spectroscopy, and photometry, and then explain how students can collect and analyze their own astronomical data. By the end of the session, we will learn how to determine a star's spectral class, identify the composition of a planet's atmosphere, and even detect the redshift of a distant quasar. These experiments provide undergraduates with valuable exposure to techniques used in professional astronomy, opening up exciting possibilities for hands-on learning and discovery. With that, let us welcome our distinguished speaker, Mr. Philip Cherian.
Nice to hear me, right? And this is clear. Yeah? So I'll stand here because a couple of things first. Oh, yeah, yes. Just one second. So when you say distinguished, sounds bad. Recently, I've realized that a phase transition has occurred. Earlier, people used to call me Bhaiya. Now they're calling me uncle. Little kids, it's becoming problematic. So age is a problem. Just a second. Let me get one of these. Yeah. And having such a broad range of interests is not something that comes easily, because everyone's very suspicious. So I'm not particularly good at anything. I'm good at doing a lot of different things. And that's not the sort of thing you'd want to emulate in the future. But it's something that sort of worked out for me, I think, overall. Sangeeta ma'am will just say how I just pointing out the first.
I want to add, you were also pet lover,
Yeah.
dog lover
Dog.
basically, and did a lot of stuff for the dogs in the college, taking them to the hospital and feeding, and so that was also part of his.
So the first thing that Sangeeta ma'am ever said to me was in second year. I never spoken to her first year. I was sitting roughly where she is right now. When she entered the class, she was teaching us college. She looked at me. What are you doing here? I'm doing philosophy. I had actually not been seen around the physics department that often back then. But okay, so just to tell you that I am not an astronomer. I have done a couple of courses in astronomy, but I'm not an astronomer. I will also be talking about history. I'm not a historian. My actual work is on disease modeling, which is epidemics, which the first reaction people have is how is that physics? It's a good question, but that's the point of a later talk. But today what I'm going to talk about is the sort of undergraduate experiments that we're designing at Astronomy. These are very cute experiments. There's nothing here that's going to be very revolutionary, but it's impressive for what we are doing from where we are doing it, not that we're doing something that nobody else is doing. And technically, many of these things you should be able to do yourself. Now, I have actually not seen the entire presentation yet, so I'm going to be as surprised as you with some of these slides. And the reason for this is because I was supposed to prepare it yesterday, but I decided that I would actually collect some data for this talk. So I spent from 6 in the evening till 4 in the morning, I was collecting data, which meant that I had no time to do my presentation, so I did it on the way here. And so if anyone tells you that as you grow a little bit older, you're going to get better at doing things, not really, you're not going to be more efficient, you're still going to be doing things in the last minute, you're going to be faster at doing them in this last minute sort of way. So that's something that that's a goal you should go for, I suspect. But don't hope that you get everything figured out. Okay, so I don't know how much time I have, so someone will please tell me about 10 minutes before I'm supposed to wrap up so that I can go through the last bit. Okay, so this is a broad outline of the talk. So I'll give you a very, very brief historical overview. I'll talk a little bit about the techniques needed for processing astronomical images. I don't know how many of you are actually interested in astronomy. Is that a thing? I mean, almost everyone is sort of interested in astronomy, right? I mean, every statement of purpose starts off with, when I was a child, I looked up at the skies, and some of you are laughing because that's what you wrote, I'm sure. Statistically, that must have happened, right? So everyone is sort of interested in astronomy. That can be a bit of an annoying thing because you actually come in and do astronomy and you say, man, I don't really like this. You like looking at the pretty pictures. There will be pretty pictures in this talk because that's the hook, but that's not all there is. There's a little bit of science behind it. So I'll talk a little bit about two techniques, spectroscopy and photometry, that we can use. Everyone should be aware of spectroscopy, right? That's something that you do in the labs, yeah. The photometry perhaps not, but we'll go through it. Interestingly, the people who know about photometry very well are my friends in advertising, because they need to worry about photometry for color temperatures and so on. These are very important things. Physics people don't seem to have. And then I'll talk a little bit of some quote-unquote backyard applications that we've done in Astronomy. So let's start off by talking about something called the third kind of astronomy. The third kind of astronomy, this is from a book in the early 1900s by Agnes Entler about the history of astronomy. She said that, look, these orthodox astronomers, the old guys, were looking at this sort of new field with content. There was this new field that of a bunch of observers who, instead of doing worthwhile things like timing transits and finding when an eclipse will occur and all of these sorts of important things, were just sitting and looking at stuff and saying, oh, how many spots are there in the sun? This is like, completely pointless. Why are we even doing all these things? So it was sort of developing as a third type of astronomy in the early 1900s, but it was not being taken very, very seriously. And it was generally like it sort of had to fight to get any sort of traction. The other types were the old-fashioned astronomy. You look at the positions, you see when an eclipse will occur, when a transit of Venus will occur. These are very important things to know about astronomical distances and so on. And then there was Newton's recent astronomy, unifying laws, finding ways in which things move, which was also very cool. But what is this irregular practitioners astronomy? And that is sort of what we would now call observation astronomy. The reason that it had a lot of trouble getting in is because we have to look at our first imaging device, and our first imaging device is the eye. Of this. So it has a focal length of around 22 millimeters, has an aperture of around 7 Oh, it's fast. Is that okay? I can keep talking. Okay, so it has an aperture, which is the pupil, the eye, the size of the pupil, which can dilate from about 2 millimeters in bright light to around 8 millimeters in dark light, so that we can get more light. And it has an exposure time of around 10th of a second, meaning that it will collect light for within that period of time. So the eye has two types of detectors. There are rods and cones. Rods are predominantly sensitive to intensity of light, so that's what you use in the dark, where you can't really tell what different colors there are. And then there are cones, which of course can give you color vision. The maximum sensitivity of the eye is actually quite interesting. It's about 1,000 photons per second, meaning that, but what's interesting is that rods and cones can actually sense a single photon. So it's not the rod or the cone that tells you that you can't sense less than 1,000 photons per second, it's the brain. So the brain doesn't want the noise to sort of overpower you. So even though the rods and cones can sense that low level, the brain will only record a signal if around 1,000 photons or so strike the eye at any given second. And the sensitivity depends on the color. And what I've drawn here, apart from the eye, this little graph that I've got here, is what we call the spectral sensitivity of the different cones. Right? So there are three of them: large, medium, and small wavelength. I think that's what they stand for, L, M, and S. And essentially, you can see that this is, and these sorts of graphs you'll see a couple of times. So this is how sort of receptive your device is to photons of a certain color. So if photons of say 4,000 angstroms came in, then none of these three things were detected. But something between 5,000 and 6,000 could be detected either by the red or the green cone. Right? Does everyone understand this graph? This is relatively simple. So how do we see fainter objects? If you need 1,000 photons per second to hit the eye, and of course your eye is not 100% efficient, so even if 1,000 photons come onto the eye, only about 10 of them actually get towards the eye. So the idea is that if you want to see more faint objects, then you need to collect more light and send it into a small region. Your eye already does that with the lens, but we want a bigger version. And so that explains why when you want to go beyond the eye, observational astronomy required the sort of advent of two different objects. The first was, of course, Galileo's telescope. But the second, which is perhaps not so obvious, is the daguerreotype. Does anyone know what the daguerreotype is? So it's the precursor to the photograph. Okay, so there are these copper plates with silver on them, treated with silver on them, and they were sensitive to light. So you could sort of expose them, and you would make an image, basically, of light if you put appropriate objects in front of them. And it was popularized by Arago, who I think some of you might know about because you've done the dynamics or something. Yeah? So we had Arago, who was the director of the Paris Observatory, and he realized that this was sort of rather revolutionary, even though at the time it was not great. Although in his writings, there's actually a very interesting thing that he says, oh, it's amazing. In good, well-lit conditions, it will only take about 3 hours for you to get a full image of yourself. So because that's how long it used to take, right? You have to wait for a long time and get that many photons because these were these were not very sensitive. There was also another problem with them, which is that when they started out, they were wet, meaning that they were only sensitive when the materials on them were wet, when things dry. And as they dried, they became less sensitive and eventually they stopped reacting. So you needed, in order to be able to take a long exposure image. I can try talking very loud if you like, and that might be easier. Is that okay? I mean, yeah? That's fine? Okay, so can you guys hear me in the back? I mean, that's fine, right? So then let's just do that and let's figure this out. Sorry. Okay, so of course we want to get more photons. One way to get more photons is to take a very large telescope that collects a lot of light and focuses into one point. The other way is to just record for a longer period of time. So the eye can record for 1/10 of a second. Maybe if you record it for 2 minutes, you get more photons, which you would. But of course, to do that, you need to have a better way of detecting sort of light. And of course, when you're doing this with astronomical objects, it shouldn't surprise anyone that the sky moves. We move, but the sky moves effectively. And so if you want to actually image an object, you'd better actually be able to track this object. And so you needed these clock drives to be developed. So a lot of things have to be developed sort of simultaneously in order for astronomical imaging to be true. And this was a photo from 1880. It does look a little bad, and it's not just a projector. This is the first photo of a deep sky image, the Orion Nebula, the first object to ever be seen. People know what the Orion Nebula is, right? Right? And it's a 51-minute exposure. And it's quite impressive that it's 51-minute exposure and you can't see too many trails in the stars, meaning that the clock drive that has been tracking the telescope is working quite well. And this was done by a man named Henry Draper. He died 2 years after this. But 3 years after this was made, we had the second photo of the Orion Nebula, and that had a rather important scientific discovery. So this is the second photo, and you can immediately see that it's a big improvement over the last one. I was going to ask a question here with the sort of suspense as well, which is that what was the big scientific discovery? The big scientific discovery was that there were stars here that you couldn't see with the naked eye. Now this is something we take for granted, but back then it was not completely known that this was the case. Now, if there are things that you cannot see with the naked eye, then there are things that only using a daguerreotype will be able to tell you about an astronomical object. That it's not that if you just stare at it for much longer, you will be able to see stuff. It showed features, it showed stars. So this was sort of giving like a firm footing to the idea of sort of observational astronomy as an important tool. So it's not just that you're counting sunspots, you're also seeing stuff that as a human being you will not be able to see, which is I think quite an interesting insight. So this is done by a guy named A.A. Commons, and his telescope actually was used until the 1980s. It was donated to UCSC in the US, and it was still used back then. But this was 60-minute exposure. So just compare this 51-minute exposure with this 60-minute exposure. Just had a bigger telescope, a much better clock drive, and much better daguerreotype to be able to do. So modern techniques of sort of modern astrophotography does not use a daguerreotype. It uses a digital sensor, and everybody is aware of it because you all probably have one in your pocket right now. You know, photography has become so commonplace. Everyone takes hundreds of photos. But you know, there's a lot of science behind that, which is interesting. So the standard digital sensor is basically made up of photodiodes and capacitors. You have an object that is sensitive to light. If light hits it, it kicks out a bunch of electrons, and then you have to do something with these electrons. So you can think of this like a tap that's sort of letting water out, and then you have to store the water somewhere. So you have a bucket, which is a capacitor that holds these electrons from the right, and then they are sort of read out. And the underlying idea is that the number of electrons that are kicked out of this is proportional to the number of photons that went in. So, of course, it may not be 100% efficient. Not every photon produces an electron, but some constant fraction of them does. And so, of course, this is called quantum efficiency, to know how many photons are converted into electrons. And, of course, general camera sensors are monochrome. They only detect light intensity, the intensity of light. But if you want to start taking color images, then what you do is you put this little mosaic on top of it, which is called a layer mosaic. So over every pixel, you put a piece of colored glass, either red, green, or blue, and that will block out all the other colors. Okay, and so when something falls in there, you say, oh, this is a green photon because no other photon could have actually gone through this. And that you have down here the spectral sensitivity for 28 different sensors. So this is from a paper in 2013, and what the solid line is the sort of median spectral sensitivity. Did someone tell me a similarity or a difference between an earlier graph that you saw? Yeah. So first of all, it looks very similar in general, and that's because these sort of digital sensors, their role is to actually mimic in some sense what the human eye sees, otherwise the photograph is not going to be very interesting. The second, of course, is that it's not exactly the same because our green and red sensitivity is actually the spectral response actually overlaps quite a bit in the human eye, but for devices they actually have been sort of spread out. So the peaks are almost equidistant. If you have questions, please just stop me at any time. Anyway, so these are the sort of spectral sensitivities of a normal DSLR camera. But astronomical cameras are generally monochrome. In other words, they use all the pixels. See, the downside of this is that you lose about 1/4 of the pixels. So 1/4 of them are green, half of them are green, 1/4 are red, and 1/4 are blue. I'll let you think about why half of them have to be green. So effectively your camera size is a little smaller. Then there are these interesting techniques that they use to interpolate between these values and so on. But in astronomical cameras, the sensors are very expensive. You don't want to waste any of the space. So what you do is you have a monochrome sensor, and then you put a piece of colored glass over the entire sensor, which is a filter. Right? So you have these different red, green, blue type filters that you put on top of this. So astronomical cameras have monochromatic sensors, and the color is detected by using something like this. This is a filter wheel. This is a camera that we have, and it has different slots for different pieces, different filters that you put on top of this. And these filters can move into place in front of the sensor. So what you can see here, even though it's not very clear, is the actual sensor. And these filters can be broadband, which are like this sort of red, green, blue, large number of wavelengths and records, and pretty flat. Notice that within the range, it sort of lets in all the light without adjusting it too much, but outside it, it goes very quickly down. And there are also narrow band, which are like 7 nanometer thick. So these are very, very sharp filters, which are only supposed to be there to let in 1 or 2 wavelengths of light. And so the spectral response, which is this particular result for cameras, is not documented for most DSLR cameras. And that's because it's proprietary, so they don't want to let other people know it because you might make the sensor as well as them. But on the other hand, for astronomical cameras, their spectral response is usually very well documented because astronomers need it in order to do any sort of real science with their data. And anyway, so this is sort of the spectral response of our cameras and the one that we're using. That's this here. So let's quickly come into the basic ideas of image reduction. By what I call image reduction is that we said that the idea is that the value in every pixel is proportional to the number of photons that hit that pixel, right? But in reality, that obviously nothing is that easy. So these what happens is these photodiodes can have electrons, and they can't tell the difference between electrons that come from a photon or electrons that come from other sources, right? And so this can add noise to your signal. And your job right now is to get a much better signal to noise. So one way to do that is to get rid of all the sources of this possible noise that could be there in your signal. So what I have on the right here is what I call a light frame. A light frame is something that I take with an astronomical camera. So it's my raw data that I go out, I point at something, I connect it to my telescope, I take a photo. Okay? So these are called lights. They are part of four other frames which I'll talk about later. And I will call these an unreduced light because I've not done anything to get rid of the noise. Okay? It's clearly a noisy image, but don't be fooled by how noisy it is. It's noisy because I've increased the contrast and gradient. That's important because astronomical data usually is very faint. So we will have to do what we call stretching. We'll have to amplify all of these details, which means that the noise also gets amplified. So you want to remove it before you do any stretching. This process of amplifying details is called. And this thing that in the center here is the ring nebula. All its features are washed out because of this high contrast that I can see. And there are a bunch of artifacts here, so you should be able to see a couple of them. The one thing that's very obvious from everywhere is that this right-hand side is extremely bright. Yeah, much brighter than the region over here, and you might think that's because there's something bright there, but actually no, this is just because all the electronics of the camera is over here, and since the electronics of the camera is there, it's heating up, and when you have this much of turbulence that make you know, when you're just sort of wiggling things around a lot, they just throw electrons left, right, and center, and these electrons get detected as signal, when in fact they are not signal, right? So that would depend a lot on the temperatures. Thermal fluctuations cause this sort of random noise, and so you want to bring that down, which is why astronomical cameras are cooled. So you have this, you bring them down to 0 degrees or -5 or -10 degrees. And in winter, I'm able to get to -5, but in this temperature, it's about 0. I think that's the best that you can possibly get. In addition, there's something else, it's a constant offset that's added to your signal. It's a little random, there are little fluctuations there also, which is called a bias signal. And the last, which is not so obvious, are these little donuts that you have. Do you see these donuts? Can anyone guess what these donuts are? It's very good. So these are what we call airy disks. You've seen diffraction patterns from small apertures, yeah? So those produce these little airy disks. So this is a particle of dust that's somewhere between the light that's coming into the telescope and the sensor, and it's a diffracting light. And so it produces these little, I mean, there are quite a few of them here, but you can't see all of them, because, but you could if you looked at it on my computer. And these things have to be removed. So the fact that there is this diffraction pattern means that the pixels behind it are getting less light than they should have been getting, which is why it looks darker. Everyone understand this? So let's look at each of these things. So I want you to look column by column. So on the left we have the dark frame, and what I've done here is I've taken a histogram of all the values in each frame. Okay? And you see that this histogram fits a Gaussian quite well, roughly. And this of course is at 0 degrees, and you find that when the exposure time is 10 seconds, you get this Gaussian over here. Now what you would want to do is remove all the contributions from statistical, from this sort of thermal fluctuations. You can't, because there will always be some amount of fluctuations. So what you can at least do is remove the mean value. So what you do to do that, you take many dark frames, you average them up. Okay, when you average them up, you will get an average value for every sort of pixel that you have there. And then you subtract that from your light frame. Now once you've subtracted that from the light frame, you will only be left with the variation here. But if you look at the variation itself, it's not too bad. The variation itself is between 234 and 238. So that's sort of four counts as error, which is sort of relatively okay if you have 4,000 of them. That's like 0.1%, you're okay with that much. Of course, the more frames you take, the better frames. Of course, if I take two darks, one after the other, and I subtract them, I won't get the value 0. Okay, you'll actually get a distribution about 0. That's the fluctuations that I've shown here. And these fluctuations are also distributed, like I said, about 0, but they also have negative values. The problem is that your cameras, in order to be fast and process data fast, they can only read positive numbers. They're integers, basically. They can only read integers. Since they can only read integers, any negative number will get flipped to 0. Which means that you wouldn't actually see the histogram, you'd only see the right-hand side of the histogram. When you average that out, you don't get the right statistics. So to fix that, and the reason that's a problem is because you're fluctuating around 0 and some of the numbers are positive and some are negative. So to fix that, what do? You just give it a constant offset to bring everything up, and then get it to fluctuate around, I don't know, 100 or some other number like that. Then when you average it out, you find 100 and you can do that. So that's what the bias is. And the third is the flat frame, and you see the airy disk much clearer here. So what we do here is we illuminate the telescope with a constant field. Right? And so this is a little cooker that we've taken and we've cut off the top, and we shoved a sort of LED inside it. and this produces a uniformly illuminated thing that we put on top of the telescope. And this produces field of light vectors. And you see two effects. One is, of course, the donuts, but the second is this circle here, which is much brighter than the region around it. And that's a process called vignetting, which occurs whenever you have your optical setup is a cylindrical symmetry, right? So whatever you get imaged out will have more intensity at the center of that cylinder and less on the edges of the cylinder. So you want to account for all of these things. Of course, remember, I increased the contrast a great deal to see this. In reality, you won't see it as clearly, but it is there. Okay, so the process is to use this formula, which is that you take the light, you subtract the dark from it, and then you divide it by the flat. I can go into this in more detail, but don't worry about it right now. There is a formula, it makes perfect sense. If you did all of this, you will end up going from the unreduced image here, which looks a little ugly, to the reduced image here, and you can see that it looks much more uniform. Can everyone see that? Right? It looks much more uniform even at this high level of contrast, because I've accounted for all these other features, except one. That feature is this little smudge here. Now this little smudge happened to be there because I was taking data, the current went off in the middle, and a drop of condensation formed on the sensor. By the time I went and took the flat frames, the condensation had evaporated. So there was a brief period of time for which there was a drop of water that could not be accounted for. And that's very important because you have to realize that particles of dust don't sit there forever. They move around. Which means every time you take your data out, when you're going out there, you need to take your flat frames immediately, otherwise your data is unusable. Okay, so that's an important thing to keep in mind. This was a mistake that I made. Luckily, it's not sitting on top of the nebula of interest, but it's just there for sort of illustrative purposes. So this, okay, I've got a couple of astronomical images. Maybe I won't show them here because they're probably not so clear on this projector, but you can come look at them on my computer later. But this is the Ring Nebula, very, very faint here. And right in the center, you see that little white dot, some of you might be able to see. That's actually a white dwarf, and we're actually being able to image. This is data that I've taken. This is the earlier Ring Nebula here. It's the data that I've taken from our roof in Soli. This, not very clear, again, it's the Cigar Galaxy, and you can also take this horsehead, which is really not clear. Come back and look at it on my computer. The Eagle Nebula, you can vaguely see the pillars of creation there, but yeah. And this is the Orion Nebula, again not very clear here, but this is sort of 140 years after Common's image. This is my image essentially, taken out again from our.
Color is a true color.
That's a difficult question to answer. So what is true color? Would you see it with the naked eye? Well, clearly from our spectral response, no, you wouldn't see the same thing. But what is red falls within the wavelengths of red. What is green falls within the wavelengths of green, blue within the wavelengths of blue. And then of course you stretch it around to get features, because your job is to see interesting features. Again, not very clear here, but some of you want to see it on my computer afterwards. You can see there's like this dust, there's features in the dust that you can actually see. Anyway, so this is one of the experiments in our lab, astrophotography. People go out, they take data, and then they learn how to reduce the images and then process it. Okay. Another experiment that I'll be talking about is not to do with just photography. So you've taken your data, you've processed it, but now you can actually do some science with it. So one bit of science that you can do is on the Fraunhofer lines experiment. Some of you have already seen this. But the Fraunhofer lines, I don't know if anyone knows what they are. Does anyone know what they are? The answer up on the screen, but it's basically there are these dark bands that Fraunhofer saw when he split the spectrum of the sun. Solar spectrum. Originally, he thought that these were going to be like the natural boundaries of colors. That this is one color, this is another color, and so on. But later on, they discovered with work by Bunsen and Kirchhoff that these lines seem to correspond to elements, because elements had emissions at exactly the same wavelengths as these guys, these dark bands. A little bit they came up with these Kirchhoff-Bunsen laws for some spectroscopy. And so one interesting thing would be, can we actually see this? And what I've done is I actually bought my little setup here. The reason I bought this is because I'll be talking about expensive equipment that we have, which is moderately expensive, not ridiculously expensive. But you don't have to have that. You can also do stuff with really cheap things. So this is a little cardboard thing that my friend Pradeep at Ashoka made for me, and it's literally, I mean, I'll show you a photo of it in the next slide. So it's just this, right? So it's got a slit that we stole from a spectrometer. Right? It's got a lens in the middle that we stole from someone else, and it's got a grating that we bought. So the entire cost is 600 rupees for one grating, and it's got an old Borosil box that we just got from the garbage, and we put it together. Okay? And if you do this, and you take it out, and you use a DSLR, you can actually also use a phone camera. It wouldn't be as good for resolution, but you could do that as well. And you connect it in front of this object. So this is a slightly different version of the same thing. So you connect it here. Inside this region, you have a grating, you're going to get the spectrum of the object that you're looking at. If you point it at the sun, you're going to get the spectrum of the sun. And this is a photograph that I've actually taken. And if you can sort of like squint a little bit, you should be able to see a couple of dark lines here, right? And so these are the lines that Fraunhofer saw. It was a big deal back then. It's still pretty much a big deal, only we don't really notice them when we look at like solar spectrum. So what can we do with these dark lines? Well, if we took a single row somewhere and we just sort of plotted that, you'd get this very noisy result up here. If you took another row somewhere else, you'd get another noisy result here. Okay? But what you can do is you can take all of these rows and say, well, they're all the same spread if I rotate them just the right amount. So every column should correspond to one wavelength. Does that make sense? So I could just average out every column so that the noise on that particular wavelength will cancel out, and you will get this result on the right hand side here. And if you look at this result very carefully, you'll see that there are these clear dips that exist here. And these dips are what we would call dark lines. So these are the locations of those dark lines. Does that make sense? Does everyone understand this? Anyone have any question? So how do we do that? Well, we crop our image, we rotate and crop it so that it's horizontal. We then remove like a background, just like in the image reduction case. We then find the mean of every column, and we end up with this. So it's just the process that I've described. Now, once you do that, and let's say I just plotted it on top of this for sort of, for the sake of comparison, you should be able to see that all these sort of dark lines here correspond to actually little wiggles in this. And all of them are related to different elements. So this is an image from Wikipedia, where you have these different, so the Fraunhofer lines were, the original ones were labeled A to F, or A to G. And then there were like hundreds of other lines that he himself found, and then other people also found beyond that. And you can actually see many of them here, and I'll show you which ones they are. So this is an image from Wikipedia of the solar spectrum, and this is the spectrum that we've seen. I've cheated a little bit here, I'll tell you later what I'm actually doing, but it sort of does look very similar. And if you look over here, for example, you see this little hump. I thought that was just something to do with our camera. Turns out the little hump is there. It's there actually in the real spectrum of the sun. But of course, everything that we've done here on the x-axis is in pixels. We don't really have a wavelength yet. So why do different wavelengths come at different pixels? Because you're using a diffraction grating. So if you want to go from pixels to wavelength, you need to use the grating equation. And if you do that, basically, so the pixels it turns out they are very nearly linearly related to the wavelengths, at least for the first one. And we do that simply by using the small angle approximation, sine theta roughly theta. If you imagine your camera to be here, a slit to be here, and this to be the pixel number of every different colored sort of column, then you can show that sine theta is roughly tan theta is roughly p by d, where d is this distance. Now we don't know d, we don't know the number of lines per mm for the grating because it might not be right. We don't know any of these things. So in general, we can say that lambda is proportional to p. So lambda is just some constant k1 times p. There's some other constant k2, where k1 is the number of angstroms or nanometers per pixel, and k2 is some constant offset. It's the location where lambda is 0. In other words, it's the location of the central maximum. Does everyone understand? It's very simple idea, right? So in principle, you can do this, and then your job is just to calibrate it. So you take this curve here, and you say, oh look, I know this little hump here. And this little hump is probably this guy, which means right at the end of this hump are the sodium D1 and D2 lines. So I use that. I say, okay, this pixel is this wavelength. Now I only need one other point, because it's a straight line, 2 points define the straight line. So I could either use the central maximum if I wanted to. If I don't, then in this case I could use, for example, this guy here is actually the G line, I think. So you could use this. And if you do that, you'll end up with what I've shown you on the x-axis here, which is wavelengths. The same spectrum, but as a function of wavelengths rather than pixels, right? So I just plotted it as a function of this formula. And what you'll notice is that I've used D1 and G to calibrate it. But once I do that, all the other lines fall exactly in their range. You see that this dip here corresponds to the F line. This little dip that I hadn't actually seen when I was doing my analysis, there's a little dip here, actually is the C line. And if you look at that, the C line is something that's created by hydrogen alpha in the sun. So this is a way of seeing that there is hydrogen in the sun. And this is using a relatively cheap DSLR camera. It's not really cheap, but it's not as expensive as most astronomical cameras. And you can sit down, take this, you can save a lot of money on this, and then you buy one camera, and you go out, you look at the sun, and you can start seeing spectroscopy of the sun. And you're using very elementary techniques that most professional astronomers also use. So we can actually go further than that, and we can look at, well, you can say, okay, fine, we did it for our closest star, but can we do it for other stars? because you can't just go around and point this at a star and hope to get something out of that, because you need to collect a lot more light. But what you can do is you can use this little star analyzer diffraction grating. Again, a relatively cheap thing, about 10,000 rupees. It's a blazed grating, and if you point it at a star, but it's slitless, it doesn't have a slit in front of it like this thing does. So if you point it at a star, you get multiple copies sort of the star in different wavelengths. And that's the little rainbow here that you see this diffraction pattern. And we could connect this to our telescope, to our camera and our telescope. So I'm not going to be using a DSLR now, I'm going to be using one of our astronomical cameras. So this image is not actually the one that I'm going to show. This is not where the data comes from, but it's just representative. And over here you have the spectrum of Sirius. Okay, so what do you notice about this? You should see that the spectrum is actually raising towards the left. It suddenly falls on both sides, here and here, but that's because the camera sensor cannot actually detect anything beyond these wavelengths. So the range of the camera sensor is something like 4,000 to 7,000. So anything beyond that is set to 0. So you shouldn't worry too much about the falling here, but you can see clearly that it's increasing at lower wavelengths, meaning that this is a blue star. That should be quite obvious, right? Because hotter objects, and that also means that it's a hotter object, because when that shows that Sirius is a hotter object, because it's bluer, and since it's bluer, if you assume it to be a blank spectrum, then its peak is more in the blue than another star like Betelgeuse, which is on the right here. And this one clearly has a peak that's somewhere here, it's going up there. And so this shows that it's a red star. But more than that, these little sharp dips that you see here are actually hydrogen dips. So these are absorption lines of hydrogen in the star. And what that tells you is that the atmosphere of the star has hydrogen in it. And this is a type A star, and I mean, if you wanted proof that a star has hydrogen, this is quite nice to be able to prove it yourself in your backyard, right? That's quite nice. On the right here, you have Betelgeuse, which is an M-type star. And you'll notice that it doesn't have these very sharp prominences. That doesn't mean that it doesn't have hydrogen. It just means that since it's an older, redder star, it has a lot more heavier elements inside it. And one of these heavier elements, titanium oxide, is known for creating these molecular absorption lines. How many of you have done quantum? Some of you have done quantum? Perhaps. Yeah, so in quantum you know that molecular degree, when you have these vibrational degrees of freedom, so molecular absorption lines are vibrational, you have equally spaced more or less absorption lines, and therefore you see these guys are roughly equally spaced as opposed to these guys here which are not. The hydrogen Barber series you should know are not. So this just shows that you can look at these different types of stars and classify them. You can compare the spectrum to the exact spectrum. So the blue spectrum here is the exact reference spectrum. And at least in the regime that we're looking at, the titanium lines are exactly matching with this other spectrum, which is actually quite cool that you can actually see this. So that's one experiment. The second one is an experiment on stellar photometry, which is counting the number of photons that a star produces. Now let's say you don't have a grating. Okay, gratings are actually problematic to use because they spread light out. And if you have very little light to start with, and you spread it out over a large region, then you're going to get, say, spread it out over 100 or 200 pixels, you're going to get 100 or 200 pixels less signal, right? So, so in order to do that, you want to get some quick results without using the grating. And one way to do that is to do photometry. Well, what we do is we take, say, the spectrum of a star here, and we take these filters. So I'm using digital camera filters right now. So you see these regions here that I showed you earlier from the 28 cameras. So I take this, and then what I do is I multiply these two things together. So if I had a blue filter and I looked at a particular star, I'm only going to be able to look at this region of the spectrum. So what I see is the integral of this region of the spectrum in the blue filter. In the green filter, it's going to be integral of this region. In the red filter, it's going to be integral of this region. So I now have, let's assume that you have a Planck spectrum. You can now find out the total number of photons in blue, green, and red, or the total energy in blue, green, and red, depending on your type of sensor. And that could give you the magnitudes in blue, green, and red. So stellar classifications have these magnitude scales. I don't know if you guys know about this, but the magnitudes are basically a logarithmic scale because you and I and everything that we know in the world right now is much more sensitive to logarithmic changes. I can't tell how many people there are here, but I know how many people there are in the first row, because I can tell like the difference between 4 and 5 much more easily than I can between 60 and 70. And that's why we have these ugly units like decibels and all these things that nobody completely understands, but we pretend and we know. But that's because, logarithms are not, I mean, they're intuitive, but not the way that we study. When we start studying detail. So, in order to do photometry, let's say I have an unknown star whose magnitude I want to figure out. And let's say I have a known star whose magnitude I know. Okay? And then what I have to do is I need to find the relative number of photons that the unknown star is producing relative to the known star. And using this piece of information, I should be able to find the relative magnitude of the target star with respect to the reference star. Does everyone understand this? It's a really simple formula, really simple idea, and it's a relatively simple formula as well. So you're just counting these different photons, and so essentially all of this is done with a little package that I made for our lab. It's nothing special, it's nothing professional. It's a baby version of professional software that you will use if you end up going on to work in astronomy. But it just does pretty much all the same stuff. So you choose a star, you plop around it, and then you start counting photons. Now you want to count photons that are within the star. How do you even know where the star ends? Now you might say, oh, I can clearly see that it ends here, but as we have established, the eye itself is not going to be something that you rely on that seriously, right? So you need to find another way to know when the end of the star is sort of being reached. And so what you can do is you could say, okay, I've got these little circles. I find the center of the star, and I start drawing circles around it and counting how many photons there are in each of these. Not photons. How many signal counts I receive from each of these circles. If ideally what should happen as I go further and further away, if you assume the star to be like a little Gaussian, at some point you're going to end up with 0. So in other words, you're going to go up and then you're going to flatten out. But if I do it here, what do you see happening? Up to 20 different pixels, which is the range here, the number is really not flattening. In fact, it seems to be growing. Right? Can anyone tell me why it's growing?
Diffraction effect is
The diffraction effect is not an issue here, because even that will eventually die out, because it falls off, right? The diffraction thing also falls off eventually. It's something very practical that I think people should sort of understand. See, what I said with the example I gave of this little Gaussian is assuming the Gaussian is on the ground. Right? But imagine the Gaussian was on this table, and I started doing the same thing. Beyond a certain point, I'm just going to keep getting the table. Right? And the area of the table is going to scale like r square as I increase my radius of these little Gaussians. So as I go very far away, I should end up getting a quadratic term, which is sort of what I'm seeing here. Does that sort of make sense? You get the sense that I'm making? Basically, what I'm saying is that the background is not zero. There is some contribution due to the background. And since there is some contribution due to the background, as you keep going up, at some point you're going to end up just with quadratic results, because the star itself contribution is died out. You've just got area that's increasing over time, and the area increases like r square, so as a function of r, it will go up like a quadratic. So we better remove this table from under the Gaussian, right? But that's going to be difficult, because sometimes this could be a star inside a nebula, and you want to remove the contribution of the nebula. And there might be like, or you could have a star or supernova inside a galaxy. So this is what we call a crowded field. I don't know how to do it for crowded fields, but if you have to do it just for sort of like not so sparse, basically sparse fields like what I'm counting here, then one way is just to say, okay, I'm going to assume the height of the table and just subtract out this value. So if I keep it too low, then I'm going to still end up getting this sort of quadratic rise, maybe a little bit later, but I'll get it. If it's too high, then I'm going to be removing more than there is. I'm going to be digging into the ground, so then the counts will increase, and at some point will then start decreasing again. And if it's just like right in sort of Goldilocks way, then you'll end up with a sort of more or less flat result. But we want to be able to do this in a more sort of scientific way. So what we have to do is sort of automatically figure out what the background is. It's a very simple idea actually. You just take all the you choose a bunch of circles and you draw around them, and you find the average value in each of these circles. Okay? To plot a histogram of these average values, there will be many of them that will be the background, and then a couple of them that will be very far away because they're sitting on a star or something else. So you reject 3 sigma of these, and you have some circles left. You repeat the process again. Sigma has now shifted. You reject 3 sigma again. You reject 3 sigma again. You keep going until when you reject something, nothing. You reject nothing basically until you reject none of the 10 minutes. So I'm nearly done. So if you reject all of these, you see that you started off with these randomly distributed circles around here, but at the end you find that you're actually not touching the star. So you want to be close to the star because you want the background near the star. You don't want to pick the background from some different region in the sky because that region has a cloud, for example. I'm exaggerating, but that's a sort of a worst case scenario where you're looking at a completely different region of the sky where the background is completely different. So you want to be close, but not so close that you pick up the star as well. And this technique allows you to do that. So all of this is done in my little language. There are much smarter ways of doing it. This is just, again, the baby version. So once you're done with that, and it gives you the average value of background clouds, and you plot the same thing again. This is for the target. You see that it goes up and it flattens out as you'd expect. So the total number of photons that the star produces is basically this number here, that the value at which it flattens out. So you integrated this Gaussian, and that's the result. And this is the total number of counts for the reference star, which I was using. And we've done this with one filter, let's say red. You now need to repeat this for green and blue. This will give us the red magnitude. Those two values will give you the green and blue magnitudes, right? So you can find all of these different magnitudes of stuff. Great, but who cares, right? I mean, that's the sum. Ultimately, that's what you're all thinking. These astronomers will come up with one weird scale. You'll figure out how to calculate something in that weird scale. So what? Can we figure out something more interesting about the star? Well, sort of yes, because so if the goal was to compute the magnitude of the star, then over here you have the theoretical magnitudes and the exact magnitudes, and you see that the values are pretty good. I mean, they're up to like 1/10% error generally, which again for a simple undergraduate experiment is not bad. I mean, most of you in your lab should know that you rarely get 1 to 10% error unless you've been fudging things. But you know, it's quite nice to be able to get values like that. But another interesting thing is we can actually find the temperature of the star. Because I mean, those of you who learned about the Planck spectrum will know that in the Planck spectrum is completely specified by the temperature, right? And so it turns out that there is an empirical relationship between the, say, the peak and the temperature. It's called Wheeler's displacement law, right? And that's something that you do. But there are other things also you can do. So one thing you can do is you can take your Planck curve and you can integrate out different regions, the blue region, green region, and red region, and then divide them with respect to each other. So green divide, how much more green is there than blue? How much more red is there than green? These questions you can ask. So those quantities are called the colors of the stuff. So you can so you can define these different colors. Now remember, green divided by red and so on, in a logarithmic scale becomes a subtraction when you divide the quantities. So you can subtract the blue magnitude from the green magnitude, blue from the red and so on. You can do all of these subtractions and you'll get 3 magnitudes, 3 colors from 3 magnitudes, right? And if you do that, you'll get these empirical curves that you see here for a bunch of stars. So let's say you take a bunch of known stars, you find their spectra, you repeat this process for them, and you'll end up with these curves here. And now you say, I have detected a star, I know its magnitudes here, using these measured values. Let me calculate the colors by doing the difference here. Now, I know that the color is somewhere here. It has to intersect this curve. So what should the temperature be? So you see that even though the colors are quite relatively different here, there's a bit of a spread here, all the temperatures seem to be corresponding to the same value because each of them cuts a different curve at a different point. And what you can see is these different values that I have here, so each of the colors will give you a different temperature. And the measured temperature according for this particular star that I'm showing you here is 7,914. The real temperature is 7,998. This is ridiculously good to have 1% error. I don't trust it yet. I'm still trying to figure out why it's this good. It's consistently good. We've been trying it out for different stars. It's worked out. I'm not sure why, but if it is true, it's quite a nice result that, you know, just sitting up on your roof, you can end up with this sort of nice. So just to finish off now, I can just show you, very quickly, you can also do this with the DSLR. You need an optical setup and a sensor, right? You don't need a telescope. You can use the camera's lens as your telescope. And this is, again, this is the sky, and again, it's very, very bad, so you can't really see it here. But these plates, I intentionally took terrible images to show you that even with these terrible images, you can get something interesting. Okay? So you see that these are this is the little sort of the little sort of bowl region of the Pleiades, and I've chosen this region in the red, green, and blue filters, and I've computed the number of photons that are coming in each of these things, computed the magnitudes for a bunch of different stars, for 4 different stars here. Over here you have the measured magnitudes, over here you have the true magnitudes, and the percentage error is well within that general range of 1% or so, which again is quite cool. You just take a telescope, you go out, you point it at the sky, you take a photograph. You take 20 photographs, you average them out, and once you're done with that, you don't need a telescope, you don't need anything, you just need a DSLR camera with a reasonably even a normal lens. This was the cheapest lens that comes with the camera. So again, something that's quite cool, right, that you can do this. But anyway, so just some other results in the last 5 minutes. This is our equipment. So this is our telescope with a student for scale. And there's another telescope that we have. So this one's called ZIP, this one's called Zoom. We've got the third one that we're calling ZAP. So this is ZAP and Zoom. These are our cameras. So the DSLR that I showed you was this, the Nikon D5600. But we have a slightly more expensive, much more expensive FPIG astronomical camera, and of course our little tweaking. So let's quickly go over what we can do. So this is the spectrum of a star called Vega. Can someone tell me what you can see about this star? Does it look familiar, unfamiliar? Looks a lot like Sirius spectrum, right? It has these very sharp dips here. That's because it's an A-class star. So if I showed you another N-class star, you'd see those large titanium lines. It's a way to sort of recognize how stellar classification occurs. Great. Here's a different type of star. This is a star called P Cygni. So these are these massive stars, and they're these extremely large stars, so that they have stellar winds and winds moving at extremely fast speeds. And so light that's coming towards you, some of it gets Doppler shifted towards you, some of it gets Doppler shifted away from you. So you have a very characteristic sort of absorption and emission line sort of pair. And these are called, it's called a P Cygni profile because it was first seen in P Cygni. And what you see over here is I've taken this particular star. You see like there's a little bright region here, slightly brighter region. That actually corresponds to this really sharp hydrogen alpha line. And there's also helium line. So one of that you can actually see that it corresponds to the hydrogen line. This is the planet Uranus, and if you have it over here, if you look at its spectrum, you can already see that there are these little dark dips. Can you see that here? Yeah. And that, when you actually when you look at it here, you can see that there are these sharp sort of molecular methane absorption lines. So just by looking at this and comparing it to the sort of fingerprint of methane that you would have from the lab, you can find that this, you can give a very good guess that the atmosphere of this planet has methane in it. And this is somebody else's image, and you can actually see that exactly. This dip here corresponds to this. Then you have this little W shape, and then you have this sharp dip here, then another W shape here, then another dip. So all the exact same things that we're seeing. Again, just this is 50 seconds, so 1 minute of exposure time, 50 images of 1 second each, stacked. So the last one that I want to show you, this is the thing that took me 12 hours last night essentially to take. So this is 3C273. 3C273 is a quasi-stellar object, it's a quasar, right? And nobody knew what they were when they were originally discovered, because if you look at it, it looks pretty much like any other star. It certainly looks a lot like this star that's like next to it, right? But when people took its spectrum, they found that there were these weird peaks here that didn't correspond to any materials at the moment. And around the 60s, someone said, hey, this looks a lot like hydrogen, the Balmer series, but shifted rightwards, like sort of transposed to the right degree. Now what causes something to transpose? Well, if it's a recession velocity, it's moving away from us, it's redshifted, right? So if we assume it to be redshifted, then you can actually find that all the lines fit. And then using that fact, by looking at the difference between the emitted and observed wavelengths of light, you can actually infer the redshift. And so that's what I've done, and I'm going to show you my results. So this is the star here, and this is very, very faint. So it's extremely faint because it's very, very difficult to see. So it took me a long time, about 3 hours worth of practical data that we had in today. Of course, that means another 3 hours of calibration frames, and a couple of other mistakes happen, and so that takes time as well. And you have to take into account all of those things. And if you do all of this together, you can find over here the spectrum of Sirius that I use as my calibration spectrum. So that's what's going to tell me where Balmer is, for example. And it tells me that Balmer is right here at 48619 angstroms. Now I take this guy and I see this little sharp, this sort of little more intense region here, and that actually corresponds to this peak here. So if I find just by eye where this peak occurred at 5628 angstroms, I take the emitted value, I take the observed value, and I get a value of roughly, again, no error bars, etc. I should be doing all of that, but I just did this in the metro on the way here, so give me a little bit of slack. But basically, this gives a value of 0.1577. The actual value is 0.158, which is ridiculously close. I mean, I cannot believe how close this is. And it's just amazing that we're able to do this with an undergraduate setup. It's slightly expensive, maybe, perhaps. So, it's possible to introduce undergraduates to key ideas in astronomy. It's sort of like actual professional astronomy, that's a possibility. With expensive equipment, not so expensive, sort of expensive. Like you can do some stuff with just a DSLR camera. You may need a motor drive. Actually, the real expensive thing for you is to be able to track the object. Because you can make up for not having a very large telescope by just looking at it for long. But what you can't do is like make up for the fact that everything's moving very, very fast. So that's something that you need to worry about. But you need a familiarity with coding, but it can be picked up relatively soon. And this can lead to sort of foundations for more advanced courses where you actually take data from Hubble or the JWST and actually analyze them. They use very, very similar techniques. The JWST has calibration frames, it has darks, it has biases, it has flats, it has all of these ideas. They process it. Your phone cameras and your DSLRs also take all of these things. It's just that they don't give it to you. They do it on chip and then they subtract all of that. So this is some acknowledgements. So this is the package that I've developed. It's a really simple, very baby astro package. It works very well for our data, which is why we use it. It's sort of part of the astronomy lab right now, which is so a bunch of students helped me sort of develop some code in it. So these two guys are usually here, but the ones they did a summer project with me, and Professor Dipankar, whose picture I should have put here, who is actually the reason that most of these experiments actually happen. And so these guys were interns, and they helped me write some code in this for photometry and spectroscopy. And these are 4 undergraduates who helped me take the data for the Quasar, because it's a painful process to carry the telescope and put it up and then set it up and then carry it and take it down afterwards and just hang around there while I go and get lunch and dinner and so on. So like this, so these are there's Rona, Karnan, Kanadi, and Kirtana. He's first year, second year, third year, fourth year. I only realized that when I was putting it into this slide right. Okay, great. So that's it. How late am I? No, 3 minutes off. That's great. Okay, so that's basically it. Yes. I don't know if there are any questions, but if you guys would like to see the astro photos, you can. Check out the little cardboard spectroscope.
I have a class.
Thank you so much, Mr. Cherry, for this enlightening session. Your insights into our observational astronomy and data analysis techniques have been truly fascinating, and we deeply appreciate your time and effort. On behalf of the Feynman Club, I extend our heartfelt gratitude to you for sharing your knowledge with us today. I now invite Sanjay sir to present a memento Mr. Philip Cherry for the token of our appreciation.
Just get this. Token.
Oh, thank you. Thank you. Thank you. Thank you.
Thank you, sir. Thank you, Mr. Philip Cherry. A special thanks to our head of department, staff advisor, and the professors of the department for their continuous support, and to all of you, our wonderful audience, for your enthusiastic participation. We look forward to seeing you at our next session. Until then, stay curious and keep exploring. Thank you.
Guys, there's refreshments outside, please.
You count him for all the information you want. You can
Yeah.
extract
Oh, also, just a couple of things. The Astronomy Society at Ashoka is